Hello students, in this video we'll discuss the Mercator projection. Consider the unit sphere. Okay. We'll do the standard parameterization R of theta and phi, and it's going to be what? It's going to be cosine of phi, sine of theta, sine of phi, sine of theta, and then cosine of theta, right? Where phi goes between 0 and pi, so 0 less than or equal to phi, less than or equal to pi, and then theta goes between 0 and pi over here, right? And so of course what happens over here when phi is equal to a constant, when we have a constant value of phi, then that means we're on a meridian, right? So when phi is constant, phi constant are the meridians, and theta constant are the parallels, right? Okay, so we have meridian and parallels, right? All right, and so of course the meridians are like the longitudes, right? And the parallels are the latitudes. And more standard parlance of block geometry in that situation, right? And so now what we're gonna do is the following. We're gonna consider a reparameterization of the sphere, right? So what I'm gonna do is this. We're gonna let V be phi, easy enough, that's just a straight transformation, so phi is not going to change at all. And what we're going to do, we're going to let the log of the tangent of theta over 2 be a new parameter over here, u, like so, okay? And so I'm changing now from the theta phi to 1 into the u coordinate. And I'm going to parameterize this. So the uv coordinates, let's figure out what's going to happen over here. Of course, it's important to remember what the tangent of theta over 2 is, right? So let's recall that the tangent of theta over 2 is the sine of theta over 2. So tangent of theta over 2, this is going to be an important thing identity for us. It's going to be the sine of theta over 2, which is going to be a what? The half angle formula for sine is going to be what? It's going to be sine of theta over 2 over cosine of theta over 2. That. Of course, I do the half angle formulas over here. But the half angle formulas is going to be just the square root of 1 minus the cosine of theta over 1 plus the cosine of theta. That. Right? I'm going to multiply by 1 minus cosine squared, right? So if we do so, what will happen over here? So that becomes what? That becomes 1 minus cosine of theta over 1 plus cosine of theta times 1 minus cosine of theta over 1 minus cosine of theta, like that. So now the bottom becomes what? The bottom becomes sine squared, and the numerator becomes just 1 minus cosine of theta over just a sine squared. So that's just going to get a sine of theta, okay? So that formula there is a half angle formula for tangent over here. That's going to be more useful because what that allows me to do is the following. So what this allows me to do is this. This allows me to write u, so the tangent of theta over 2 is going to be e to the u, like that. And that says that 1 minus cosine of theta over sine theta is going to be equal to what? It's going to be equal to e to the u. And so now I'm going to write cosine squared theta. So let's let s capital, be just the sine of theta. Okay. If we do this, what's going to happen? Then the numerator becomes 1 minus the square root of 1 minus s squared is going to be equal to e to the u times sine theta, right? So I'm an e to the u and then sine theta. Sine theta like that, which is just going to be s. Where is s? Now I want to solve this equation for s, right? S over here. And so what we'll do is we'll do the following. So I'm going to write this as s. Good. And so we're going to write this as e to the u s minus 1 is equal to negative square root of 1 minus s squared, like that, just by subtracting the 1. And therefore we get what? We get a total of e to the 2u s squared minus 2 e to the u s plus 1 is equal to 1 and then minus s squared, like so. Good. And so now, of course, the 1s are going to cancel out over here. And then that allows me to write the following. So one of the s's will cancel, so I'm going to have an e to the 2u, and then a plus 1 times s, the sine of theta, is going to be equal to what? Is going to be equal to just a 2 e to the u. 2 e to the u. And so that says that the sine of theta, s of course is the sine of theta, is going to be what? Is going to be 2 e to the u over e to the 2u plus 1. If we scale the top and bottom by e to the negative u, then this becomes 2 over e to the u plus e to the negative u, and that's just going to be the reciprocal of hyperbolic cosine, so that's hyperbolic secant of u, like that. Excellent. And of course, what's that going to force the cosine to be? That's going to force the cosine to be just the hyperbolic tangent of u, right? So in other words, this is for the cosine of theta to be hyperbolic tangent of u. And so now we have our reparameterization over here. Great. And so remember that phi is equal to v, so now we have our parameterization, which is going to be what? So parameterization r of u and v is going to be what? It's going to be cosine of v, sine of theta, but the sine of theta is really what? Sine of theta is going to be the hyperbolic secant of u, so it's going to be hyperbolic secant of u, and then the sine of the cosine of v, then hyperbolic secant of u, and then you're going to have the sine of v, and then finally you're going to have what? You're finally going to have just the cosine of v, which is the hyperbolic tangent of u. And what this mapping is called the Mercator projection. This is the Mercator projection. Okay. And what's the key? There are two key features of this Mercator projection. What's happening over here is really taking the sphere like this. There's the unit sphere. There are my parallels like that. Parallels. And then meridians like that. So they're my parallels and there are my meridians like so. And so what we're doing is we're reparameterizing it. And so now we're in the UV space. So here's U and then here's V like that. And so what's happening? So when U is equal to a, so let's see what happens when V is equal to a constant. So when V is equal to a constant, that corresponds to what? That corresponds to phi equal to a constant. So P equals constant corresponds to the velocity. And of course, what does V go between? V goes between 0 and 2 pi over here. So we're on this strip over here. And what does U go between? So U, of course, is the log of the tangent of theta over 2. As theta goes between 0, the tangent of theta is going to be 0. The log of 0 is negative infinity. If I plug in pi, the tangent of pi over 2 is equal to the tangent of pi over 2 is equal to positive infinity, log of positive infinity. So we're going to get the whole range of values for u over here, but the v is limited over here in this strip, like that. So we're in this strip. Of course, when v is equal to a constant, so d equals constant over here corresponds to phi equals constant. When phi is equal to constant, you have the meridians over here. So that the meridians are being mapped into these lines over here. And what about the parallels? When u is equal to a constant, that's going to force theta to be a constant, right? And theta is equal to a constant is going to correspond to what? Theta constant corresponds to the parallels over here, right? So parallels go over like this. So they're my parallels. Okay, so in other words, meridians and parallels move to straight lines, right? So meridians and parallels are mapped to straight lines. Okay. And you might say, well, that seems like sort of a strange thing to do because the sphere has a natural curvature to it, right? But if you look at any map of Earth basically, I shouldn't say any map of Earth, but most maps of Earth are maps of Earth on a rectangle. If you go into Google and search in maps of Earth, you're going to see a rectangular version of Earth. And what they're doing is they're using Mercator projection to project Earth in terms of longitudes and latitudes onto a sheet of paper, basically, right? So in other words, when you're trying to make a map of Earth, you don't want to have a three-dimensional sphere as your map of Earth, right? You like to have basically something you can put on a page, and that's what this Mercator projection does. Okay, so it maps meridians and parallels onto straight lines in UV space. Now, the other thing to consider is let me consider the first fundamental form of this. So we do the first fundamental form. Let's look at r sub u. That's going to be what? The derivative of hyperbolic secant is negative secant hyperbolic, tangent hyperbolic, cosine v. Same thing over here, negative secant hyperbolic, tangent hyperbolic, sine of v. And then hyperbolic secant quantity squared, like so. What's my r sub v? R sub v is going to be what? It's going to be negative hyperbolic secant, and then what? And then sine, of course. And then positive hyperbolic secant cosine of v. And then there's no component over here, right? So what's my first fundamental form going to be? So if I look at ru dot rv is going to be what? Well, it's going to be secant squared tangent, and then cosine sine, secant squared tangent, hyperbolic secant squared, hyperbolic tangent squared, sine cosine. So those terms cancel out. So there's no cross terms over here. If I did rv dot rv, I'd have secant, hyperbolic secant squared, right? So in other words, my first fundamental form over here, so 1, it's going to be ru dot ru du squared plus rv dot rv dv squared. That's my first fundamental form. Now if we do ru dot ru, what will it look like? It's going to look like this. It's going to look like, what are we going to have over here? We're going to have a hyperbolic secant. So we'll have this thing squared over here, and then this thing squared over here. So that's going to be a hyperbolic secant squared of u, hyperbolic tangent squared u, plus hyperbolic secant to the 4th of u du squared plus hyperbolic secant squared of u dv squared, right? Now, of course, if I plot the hyperbolic secant squared from these things, I have tangent squared plus hyperbolic tangent squared plus hyperbolic secant squared, that's equal to 1, right? So in other words, this thing just will simplify. This whole thing just simplifies to hyperbolic secant squared of u times du squared plus dv squared. Beautiful. Now, the important part about this now is the following. What this allows me to conclude is that this shows that this metric over here, that this is a conformal metric, right? So in other words, this is conformal metric. And what that means, it's conformal. Okay? Conformal means that the angles between curves over here, so if I draw 2 curves on the surface over here, and I compute the angle between them, and I look at the same curves over here in the Mercator space, then the angle between those 2 curves is preserved by this mapping over here, by this reparameterization. So it's an example of a conformal mapping. So in other words, that's really beautiful over here, because what you want to do now is what we're going to consider in further videos is that if I look at very special sort of trajectories on the sphere, which are called loxodrome or rhumb lines, those are lines that basically make a constant angle with respect to meridians. So you might say, why would I care about something like that? That's the easiest path of navigation on the sphere, right? We know from our theory of geodesics that the great circles are the geodesics, right? So if you want to go from point A to point B in the sphere as fast as possible, you follow the great circle, right? But now what's happening as you move along a great circle is you're constantly changing your what? You're constantly changing your meridional angle. Now, if I'm basically going to fly along a loxodrome or a rhumb line, that means my bearing is constant. Of course, that's going to be a longer path per se, but it's easy from the navigation perspective, right? So, of course, if you want to, you're not concerned about, conserving fuel, or if you're not concerned about time, then all you care about is an elementary way of flying from point A to point B. These rhumb lines or loxodromes are the way to do it, because you don't change your bearing at all. It's just basically saying, I'm going to go straight on the freeway. However, if you basically want to do the fastest possible, we already know that the great circles are the way to do that. So in further videos, we're going to write down the differential equation for these rhumb lines or loxodromes, and we're going to say they correspond to straight lines over here in this Mercator projection space. Thank you very much.